So we're going to do something pretty hardcore here. We're going to look at a proof of the power rule for differentiation. So if you've been doing some differentiation, you might have realized that you bring the power down, you leave the x there, and then you decrease the power by 1. This video is going to explain why we do that. And I'm going to step through exactly one proof of this power rule for differentiation. So let's jump into it. There's a few key things you need to know on the outset. One of them is what the first principles definition of the derivative is. So I'll put a link below to another video to explain where this comes from if you're not sure. But basically, the derivative of a function is defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. And so what our job is in this video is to say, okay, if f of x equals x to the n, find f dash of x. What is the derivative of this? And we should get something like n x to the n minus 1, because that is generally how we apply the power rule for differentiation. So let's jump into it. It's going to be pretty tricky, but we'll give it our best shot. So if this is our function x to the n, well, we're going to substitute that into the first principles definition of the derivative. So it's going to be x plus h to the power of n minus x to the n all over h. So basically, wherever there was an x, we put x plus h, and then we just take away x to the n all over h. So sort of subbing x to the n into that formula for the derivative. Okay, this is where it's going to get a bit more interesting. Let's just take an aside here for a moment to really wrap our head around a few things. If we thought about the question x plus h to the power of 0, we would say that that equals 1, because anything to the power of 0 is 1. Let's look at the next one. X plus h to the power of 1. Well, that just equals x plus h. Anything to the power of 1 is just that thing, right? Right, then it gets a bit more interesting. Then we get a binomial product where we have to multiply something by itself. So we get x plus h all squared. So hopefully be aware that if you expanded this out properly, you get x squared plus 2xh plus h squared. Okay, if we did x plus h cubed, take my word for it, I'll get a pen and paper out and expand it, but you get x cubed plus 2x squared h plus 2x h squared plus h cubed. And finally, if we did one more step, x plus h all to the power of 4, you would get something like this. And you're probably wondering why we're even talking about this. Well, the reality is, if we look over here, we've got x plus h to the n. So we need to think about these types of patterns that are going on in this, in these expansions here. And we could obviously keep going. So what we are going to talk about is how we could work these expansions out a bit more quickly. And this is where we're going to introduce we're going to introduce Pascal's triangle. Basically, Pascal's triangle tells us the coefficients of our expansion. So let me explain. On this first row, we're at this level here. So anything raised to the power of 0 is 1. So our answer here is 1. Okay, anything raised to the power of 1, a binomial raised to the power of 1 has coefficients of 1 and 1. So it's 1x plus 1h. So Pascal's triangle says you raise something to the power of 1, coefficients of the terms will be 1 and 1. And hopefully you're getting the idea. If we go to the next row of our triangle, now it tells us the coefficients. So we're going to get 1x squared plus 2xh plus 1h squared. And the way we get the next row of our triangle is we add the adjacent elements that are above each spot. So we get 1 plus 1 gives us 2. 1 plus an imaginary 0 over here gives us 1. 1 plus an imaginary 0 over here gives us 1. So the next row will be 1. 1 plus 2 gives us 3. 2 plus 1 gives us 3. And then a 1 here. I encourage you to think about what the next row of the triangle is, but it would be this 1, 4, 6, 4, 1. So let's look at x plus h to the power of 4. Let's look at the coefficients. 1, 4, 6, 4, 1. And now let's look at the powers. It goes x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0. And the h's go in the opposite direction. H to the power of 0 here, h to the power of 1, h to the power of 2, h to the power of 3, h to the power of 4. So that's how Pascal triangle sort of helps us understand how to expand these binomials. Okay, we're going to take it one step further in order to understand this, and we're going to say this. This is another way to represent Pascal's triangle using a function in maths that's called the choose function. Okay, so this is basically Pascal's triangle set up again, and we would, to read this, even though they sort of look like fractions, you'll notice there's no vinculum, there's no line in the middle, so these aren't fractions, but what we would say is 0, choose 0. And one way to think about that is, how many ways are there to choose nothing from no objects? Which is a weird way to think, but there's one way to choose nothing out of no objects. Okay, so that's that one there. Okay. How many ways are there to select, to choose one object? I'm going to make sure I get it right. Let me get the phrasing right. One sec. Yeah, so if we have one thing, like the letter A, for example, how many ways can I choose none of those letters? Well, there's one way to do it. So that's why this is a 1. So 1 choose 0 is 1. Okay, similarly, just think about a list. Just think about the letter A, so just some object. How many ways can I select one thing from that one object? Well, there is one way to do that. I can only select the letter A. All right, 2 choose 0. So now I've got two objects. How many ways can I choose none of them? Well, there's one way to do that. I can have the letters A and B. How many ways can I choose none of those? Well, there's one way to do it, by selecting none. Okay, if we go to the next one, 2 choose 1. All right, so now I've got two objects, A and B. How many ways can I select one of them? Well, I can select the A or I could select the B. So there's actually two ways. So that's why this is a 2. You'll notice you get 1s all down the side, and then you get these other numbers filled in on the inside of your Pascal's triangle there. Okay, so there's a fair bit going on here. So what we actually need to do now is we need to link this back to our derivative over here. So let's look. We're going to get this monster. Well, let's break things down a little bit. If we were to expand x plus h to the n, well, what that means is the first thing we're going to get is going to be n choose 0. Okay, because from that power n, we're choosing none of them. And let me just think how to explain that better. All right, so this is a better way to explain it. So with this first term, so for example, let's look at x plus h squared. Our first term is x squared. So if we think about what the coefficient of that is, the coefficient of all of our first terms is 1. So in Pascal's triangle, we're kind of down this side of the triangle, right? Or down here, we're down this side of the triangle. So we're saying n choose 0 will be the first coefficient, or n choose 0 is 1. All right, then you're going to get x to the power of n, because remember, your x value starts with the highest power. So for example, x plus h cubed, you start with x cubed. Okay, and then you move along your Pascal's triangle. So then it's going to be n choose 1. That's always in the second position, right? As you start to move across your triangle, we're now going to be at n choose 1. Okay, so that's going to be multiplied by x to the n minus 1. Okay, remember, all the x values decrease by 1 each time. X to the 4, x to the 3, x to the 2, and so on. But then a h gets introduced, right? In the second term, which is here, a h gets introduced. Okay. Similarly, we go to the next term. We've moved along in our Pascal's triangle. We're at n choose 2 now. Okay. But our power of x is decreased by 2 because we're into the third term now. And our power of h is increased by 1. As you can see, x's go down, h powers go up. Okay, and eventually you're going to keep doing that until you get to the end row of your Pascal triangle. So you're going to get to n choose n, right? And then you're going to have h to the power of n. So look here, x plus h to the power of 4. Our final term is h to the 4. So our final term going to be h to the power of n. Now this minus x to the n here is because of this part here, subtracting x to the n. Okay, so if you can understand that step, you're doing very well. So let's think here. What we're going to do now is minus x to the n. This first term, n choose 0, anything choose 0 is 1. So this first term is just x to the n minus x to the n. So they're going to cancel out. So this and this are gone. And then what we're going to do is we're going to take out h as a factor, because we're going to have this term and this term and this term. So we take h out the very front, cancel the h with the numerator and the denominator. So we're just left with this term here and this one, and then all these other terms all the way up to n choose n, h to the n minus 1. Okay, and finally, believe it or not, that all simplifies to n x to the n minus 1. But hopefully that's not too surprising. N choose 1, anything choose 1 is itself. 2 choose 1 is 2, 3 choose 1 is 3. So this first thing here is just n, x to the n minus 1. Okay, all these other terms have h's in them. All these other terms have h's. This has got a h, this has got a h. And if h is approaching 0, so you're getting the limit as h goes to 0, then these terms fall out and you're just left with this first term. So that's a proof of why the derivative of a function x to the power of n equals n x to the n minus 1, which is a rule you'll use often. And this is the reason why the rule is the way it is. And this is only one way to prove it. There is lots of other ways, but for me, at the moment, this is the most understandable. So hopefully that made some sense for you.